fragments and blast. Not bullets, it is fragments. The ceramic composite armor paradigm built around stopping rifle rounds have been overtaken by events. Wide area coverage now matters more than peak V50 parameter. And India's gap is the Army's cumulative BPJ contract covers roughly, till now what we have procured till now is approximately 2.5 lakh sets. This is the data from the open source. Against a declared requirement of 10 lakh, modern body armor has been shown to reduce fatal torso injuries by over 90%. From the studies of Vietnam, where it was 70% fatality rate in Vietnam War, to under 5% in modern recent conflicts. That means modern body armor is effective. That reduction is what we are leaving on the table. This talk is the material science roadmap to close that gap indigenously. Let me start with what the battlefield actually asks of our armor systems. The soldier's adversary is no longer one-dimensional. The table you see is a threat taxonomy of that spans from drone fragments to kinetic energy penetrators, and the protection technology for each is fundamentally different. At the low end is FBV drones, fragments, grenade, mortar sharpener, a soft armor, yoke, collar and deltoid protector stops them. This is the dominant threat in Ukraine today. In the middle is rifle armor piercing and hard steel core rounds. This is what our soldiers face on daily basis in J&K CICT. A hard ceramic SAPI. SAPI stands for small arm protective insert, the bulletproof plate what we insert in the jacket. Boron carbide or silicon carbide backed up by UHMWPE defeats this. This UHMWPE, I'll be using this word again and again. This is the backing material, organoplastic behind the plate. The material which is near to the body, between the body and the plate. At the vehicle level, we have 125 mm armor piercing fin stabilized discarding SABO, that is AFPSDS, kinetic energy penetrator, the domain of Kanchan composite or Arjun. At the CBRN end, gamma radiation, chemical agent, tungsten nanoparticle, composites are the frontier response. So what the paradigm shift has taken place from Ukraine lesson is not that we need hard ceramics. It is that we need wider coverage. The average injurious fragments weighs around 0.6 gram to 1.2 gram and travels at the velocity, roughly at the velocity of 1000 feet per second, that is 304 meter per second. That is not an armor piercing problem, it is a coverage problem, and helmet, yoke, groin, deltoid, shin guards can handle this. And we have a unique challenge, dual challenge in fact, and no other army in the world must simultaneously equip for Siachen at minus 40 degrees Celsius and in Thar Desert plus 50 degrees Celsius. That is 190 degree thermal operational span envelope is a design constraint that no foreign BPJ or vehicle armor has been validated against. With the threat defined, let me take you into the physics of how we defeat it and why ceramics and the physics of its defeat of the rounds. There are 4 steps into it. I'll just briefly touch upon them. First is the impact. The ceramic phase with a viscous hardness of 28 to 34 gigapascal immediately begins to erode the hardened steel core of the projectile. The ceramic is harder than the penetrator. That is the first and foremost critical fact. Erosion. The elastic modulus of boron carbide 360 to 400 gigapascal transits the impulse radially, dispersing kinetic energy in a cone. The projectile nose is blunted and shattered. The third is the fragmentation. Both the projectile and ceramic fragment energy is now distributed across multiple lower mass fragments, traveling at lower velocities. And the arrest, the backing, what I said, UHMWPE or organoplastic backing that catches the fragments cloud and mitigates behind armor blunt trauma that the body will face. Look at the table. Draw your attention to boron carbide, B4C, the third one in the row. Hardness of 28 to 34 gigapascal and density of only 2.5 gram per cc. Compared to RHA steel, it is which is approximately 2 gigapascal hardness and 7.8 density. This boron carbide is 14 to 17 times harder than RHA steel and 32% of its weight. Why I'm talking about this is, you'll see in the next slides. That's asymmetry is what makes ceramic composite armor possible at human portable weights. This is why Abhed uses it, and we'll talk about Abhed in the next slides. This is India's ceramic of choice. The last one, the second last is aluminum oxynitride, a transparent ceramic sintered at 1850 degrees Celsius. Bending strength is 255 megapascal, and 19.9 gigapascal is the hardness. And it goes into armored vehicle windows and aircraft canopies without sacrificing ballistic protection. Now, given this physics, how does geometry amplify the material's performance? It is not only the material, but the geometry also affects a lot. Same material, different geometry, dramatically different operational outcome. Architecture is the force multiplier that material science alone cannot provide. The baseline is the layered composite ceramic strike face, organoplastic backing, RHA sandwich, and it is 46 kg per square meter. And the baseline drops to 36.7 kg per square meter when we put a screen. This is modification we are giving to the simple ceramic plate, which means that 20% weight reduction for identical threat defeat. 20% lighter means 20% more mobility, 20% more time before musculoskeletal injury that will degrade the combat effectiveness. Second is the hexagonal cylinder array. That kind of architecture is also possible. Instead of a monolithic tile, a close-packed honeycomb of ceramic cylinders. Each cylinder focuses strength on the projectile tip, designed for 12.7 mm HMG defeat, the Dushka and Chinese equivalent of QJ-89, the threat on both sides of our active border. Failure of one cylinder will not propagate to the next one. That means it is giving the true multi-hit capability. The third one is the bio-inspired fish scale. There is a study in 2024, and it involves overlapping silicon carbide plus that UHM WPE backing composite scale, biomimicking the fish armor. Finite element method has been validated and flexible. What advantage it gives is the flexible, conformal, multi-hit protection over curved body surface, not available from flat SAPI plate. And the fourth one is ceramic mosaic. The fourth architecture directly answers the question every commander asks: what happens on the second hit? And that is very important to know, that a monolithic plate is one structural unit. One round creates a fractured cone that compromises the surrounding area. The second hit in that zone meets a partially defeated material. A mosaic array breaks that propagation chain. Each tile is bonded through a compliant polymer interface. When one tile fractures, the adjacent tile does not know it happened. Ukraine data shows that 2 to 3 impacts within 100 mm of radius is now a common scenario. Against a monolithic plate, the third impact is effectively unprotected. Against a mosaic array, it is not. India has no indigenized mosaic ceramic array in production or in qualified specifications. The ceramics, boron, and silicon carbides are available. The funded qualification program is not. That is research priority that will be flagged in the last. Let me now move to the textile and soft armor component of the protection system. Hard ceramics stops the bullet, soft armor stops the fragments, and the covers covers where rigid plates cannot move. Look at this chart. The Kevlar at the bottom of 49, it has got value of 232 centinewton per tex. This is the unit which measures, which is used for the fibers to measure their strength. The global baseline for 30 years, the Kevlar we have been hearing in every form. Kevlar 149 is at 295. The Russer C, a Russian third generation high performance aramid fiber at 565. See the difference. That is 2.5 times stronger than standard Kevlar. And let me tell you that DMSRD Kanpur is working in this space. The requirement is to accelerate Indian fiber performance to this benchmark. The architecture matters as much as the fiber. A 90 and 0 degree bidirectional layup is consistently the most effective because fragments arrive from any direction. The fiber network must arrest motion in all directions simultaneously. The matrix material is a procurement decision, not a science decision. Same fibers, same weight. Thermoplastic matrix gives 538 meters per second V50, whereas epoxy gives 391, 38% improvement, and by changing only the binder. That is the specification lever available today. So that means that we have to be very aware about that the same material, if the specifications and structural changes are made, the improvement can be done in the outcome. One more point which is very important, the natural fibers. The last card on the right side, and Kenaf and Kevlar hybrid achieves 590 meter per second ballistic limit. And this is homegrown in Maharashtra and Karnataka. Piasawa reaches 272 joules energy absorption. These are not exotic material, they grow in our own country. And untapped indigenous feedstock for armor that warrants a DRDO and academia joint programs. Let me now take you to the frontier, what happens when armor goes to the molecular scale. We have talked about a lot in the first two sessions about nano and nano materials. I'll just touch upon about one material, that is CNT, whose Young's modulus is 7,000 gigapascal. That is the modulus of carbon nanotube, 35 times stiffer than titanium at a fraction of the weight. The theoretical implication is 15 to 35 times reduction in armor thickness. The manufacturing at scale remains the challenge. India's nanotechnology establishments working in this field is positioned to contribute. A magazine, one material, and three functions, which I myself have worked in the field of EM shielding, and it can give structural strength also. The real-time structural health monitoring is also possible through this. So one material, three defense functions, direct relevant to command post, shelter construction, and vehicle armor protection electronics. Radiation shielding, tungsten